All right, so welcome back, everybody. And we're doing week 5 of service security. All right, and this week we're going to enter into the modern, closer to the state of the art of modern symmetric key cryptography. So that's today's topic. So what was the assignment for this previous week? For this previous week, you had this coding assignment where you had to write your code for these basic symmetric key ciphers that we've discussed so far: Caesar, double permutation, and one more. What was it?
Just those three.
Caesar, permutation, and? Oh, yeah, double transposition. Okay, all right, thank you. I'm losing it. All right, great. So, and we get a sense of some of the important things that are going on in cryptographic algorithms. I'd like to put it all together and also race ahead really fast to the state of the art to kind of show you like how crazy it's gotten and what we can do about it. All right. So today we're going to talk about modern symmetric key cryptography. And remember, symmetric key. Why do we use the word symmetric? What's so symmetric about the key? What's that? Say it, Billy. Okay, what is the left and the right? It's your, well, what do you mean by left and right? When you are encrypting, the key that you use is the same key you will use on the right when you are decrypting, right? Is that what you mean? Okay, good. So that's exactly what we mean by symmetric key. It's the same key we're using to encrypt and decrypt. Why would you use any other key? We'll talk about that next week, all right? But let's talk about the state of the art, well, closer to the state of the art, okay? So, a couple of things. Ever since World War II, but before that, but ever since World War II, there's been a crazy arms race to develop better and better cryptographic ciphers, and there's a crazy arms race to break cryptographic ciphers. So it's a very competitive environment in which cryptographers, who are primarily, I suppose, mathematicians, but they are in the applied field of cryptography, are trying to develop really incredible ciphers. And also, it's not just mathematicians and cryptographers. It's also the people who are in charge of modern technologies. Like if you're developing a new IoT device or a new wireless protocol, if you're on that committee, you have to choose which cipher you're going to use. So not only you depend on cryptographers to develop ciphers, we also depend on these agencies who are developing these protocols and technologies to apply the correct ciphers, okay? And on the other hand, the same cryptographers are also trying to break all the other ciphers, all right? Why are they trying to do this? Well, it's part of the academic process, is part of it, is that cryptographers are researchers, so they're trying to develop and break at the same time, all right? Continuously improve the state of the art. So for example, this is just a tail end of one of these stories. So in the wireless communications area, various different ciphers have been used and broken over time. One of these stories looks like this. The A53 algorithm was used for 3G networks as of 10 years ago. It was released. And within a few hours of it being released and announced as one of the official ciphers for 3G communications, wireless communications, within a few hours of that, it was broken. And scientists released a crack on how to defeat that cipher, all right? And later on, we now have other ciphers like SNO 1.0, 2.0, SNO 3G. These are ciphers that are now used for 3G, 4G. I'm not sure about 5G, at least for 3G and 4G communication. There's actually at least 3 or 4 different ciphers being used by different operators and network providers for these different, for 3G and 4G, okay? Most of them have already been broken. SNO 3G, as far as I know, is not known to be broken, all right? But the older family of A51, A52, A53, at least A52, A53 were broken. Interestingly, there's politics at play also. A51 was the original cipher for GSM, for 3G communications. And the United States, I believe, encouraged cryptographers to come up with another one called A52, which was known to be weaker, but they wanted that to be more like the export variant. They wanted a weaker version. For some countries wanted a weaker version that they could break easily so that they could keep tabs on their citizens. All right, so there was a cipher built that could be broken. Bit bizarre. All right. A53 was supposed to kind of give us a new solid one, but it turned out to be weaker than A51 in many ways. Okay, but A51, A52, A53 are all believed to be broken. Do you guys remember the story of Edward Snowden? He was the CIA operative who came out and leaked all the story about the CIA. And one of the things he said is that, for example, A51, the US National Security Agency can listen in live and break that in real time right now. So these are not to be trusted. All right. Okay, so but I just want to let you know that there's this arms race going on, because I'm going to show you a whole bunch of ciphers today. We're going to really race ahead with showing you ciphers, and I want to make it clear to you why we're developing all these ciphers. It's because we keep finding deficiencies in some and developing new ones. Okay, so I'd like to kind of go through several of them as quickly as I can. All right, cool. Let's start with, we're going to start by talking about a whole class of symmetric key ciphers, which are known as stream ciphers. All right, and you maybe have a taste of this, but let me kind of give you the basic understanding of this. So remember, we talked about that one of the problems with ciphers is that with modern ciphers is you cannot reuse the key, right? So we saw, for example, with the one-time pad, you cannot reuse that key ever, not even once. So what do? I mean, do you keep transferring keys all the time to each other? Like, what do you do? Stream ciphers is one attempt to solve this problem. And the idea of the stream cipher is that you don't just have a key, you have what is called a key stream. Okay? A key stream is an infinite stream of bits that forms your key. So your key is not like this fixed, it's not a fixed key. It's continuously changing, like a river flowing past you, right? It's continuously changing. And so the idea of stream ciphers is to introduce this key stream that is continuously changing bit by bit, all right? Here's an example of it. So I was mentioning the A5 family of ciphers. A51 was one of the first ciphers made for 3G communications for cell phones, all right? And here's the idea of it. So how do they develop this key stream? The way that A51 does it, it has these three registers. A register is just a collection of bits. Each register, the bits are numbered 0 through 18, 0 through 21, 0 through 22. Okay? So there's three sets of bits of different lengths. And what happens is, every time we want to generate a new bit of the key, all right, what happens is that we just shift all the bits in the registers over by one, all right? And at the end, the last bit of each register, like bit 18, 21, and 22, will get exclusive ORed together, and they will collectively, once they're exclusive ORed together, they will form the new bit for the key, all right? So we can keep shifting these bits down, and at the end, we're exclusively ORing them to getting a new bit for the key. And we can use that bit for the key to do what? To do a one-time pad. We can use every bit of the key, we can use it with one bit of the plain text, and do an exclusive OR to encrypt our information, all right? So this is the one-time pad, but the trick here is, it's not a fixed key. We now have a stream of bits coming infinitely, all right? So we can keep encrypting it like this. How about the people decrypting it? Well, they have to start with the registers at the same position as you, and the person decrypting it on the other side of the communication, they have to develop this key stream in synchronous with you, all right? They develop the same bits at the same time as you, and they decrypt as you are encrypting. So this is the idea of a stream cipher. Any questions? Ed, any question?
Yeah, the last bit, could you elaborate a little more?
On which part? The encrypting or the decrypting or both?
How are they doing it simultaneously?
How they're doing it simultaneously, fantastic. How they're doing it simultaneously, so to begin with, they have to agree on what bits they start with in these registers, okay? So they have to have some agreement. I'm not going to go into how the 3G protocol will take care of that, the GSM protocol will take care of that, to make sure that the two recipients know that, okay, we're going to start with the same bits in these three registers. Now we will all do the same operation to produce this key stream at the same time. So every time you encrypt a bit and send it to me, I will produce one bit of the key stream, which is going to be the same as yours, and decrypt it. All right? So that's how they're doing it. All right? So this is the idea of the key stream. Yes, question?
We're a little bit confused about
Confusion.
how it works.
About how, so do you understand how this key bit is generated every time? We just take the registers and we just push all the bits to the right one. The bit on the end here pops off. It's exclusive ORed with the bit that pops off here, that pops off here. Okay? So we're just shifting all the bits over one. I'll get to what happens to the other bits in a moment, but we shift them all over one. The bits that come off the end, we exclusive OR them together to generate the next bit for the key. All right? Does that make sense, Yanu?
So why is 13, 16, 17, 18 do exclusive?
I'm going to get to that in a moment. Yes, I'm going to get to that right now. But first, I want to make sure you understand how this key bit is generated and how it's used for the encryption. You're okay with that? Yes? Okay. So then what else is going on here? Well, if we're shifting everything over right one, what happens to bit number 0? Right? Like that gets shifted into bit number 1. What's the new bit number 0 then? Do we just put a 0 in there? That's not good. So we have to generate a new kind of pseudo-random bit for this first bit every time we shift them over. And the way we do it is we pick a few bits in the register, like 13, 16, and 18, 13, 16, 17, and 18. We exclusive OR them together, and together they become the new bit number 0. All right? So we are shifting these registers over, creating new key stream bits, and at the same time, we are regenerating the bits from the beginning as well, using the bits that are already in the register. All right? So this is how this key stream is generated. All right? All right. Any questions about that? Yeah.
So it's regulated to use 13.
Yes, those are fixed. Those will be changing every time. I mean, but those positions are fixed. Okay, those positions are fixed. Why those bits? I don't know. You'd have to ask a cryptographer. You'd have to ask somebody who found this is the mathematically best way to do it. All right. Great. All right, moving on. So this is how a stream cipher looks like typically, and this stream cipher is producing a key stream of bits. Okay, so it's producing 0 and 1s continuously. There's other ciphers. So remember, A51 is used for, was, or maybe sometimes is still used for 3G communications or 4G communications. Another cipher is called the RC4 cipher. It's also producing key bits, but it's not doing it a bit at a time. It's doing it a 1 byte at a time. A byte is 8 bits. So it's doing it 1 byte at a time instead of 1 bit at a time. Okay? And the algorithm is here, but I'm not going to go through it. But essentially, you're going to see some things that might be familiar to you in here. All right? There's like modulo math and other things going on. But the basic idea is rather than producing a key stream bit by bit, it's producing it byte by byte. All right? The RC4 cipher was used in very early HTTPS or SSL. And it was also the cipher that was used for WEP Wi-Fi. So you know nowadays when you connect to the Wi-Fi in the room, you typically see something like, please enter your WPA password. Like there's a protocol called WPA. Before that, it was something called WEP. That was what we used. In fact, as of 10 years ago, when I started teaching the class, when you set up a router, you would be asked, do you want to set it up as WEP or WPA? All right. So WEP was the earlier protocol, and this used this RC4 cipher, which is again a key stream byte by byte. All right. So interesting. So they're basically using the one-time pad, but the trick is, since you cannot reuse the same key, they're continuously developing new keys, and the recipient has to develop the same keys at the same time as you. All right. So that's the trick that's going on in here. All right. Great. Okay. Let's talk a little bit about confusion and diffusion. Remember, confusion is about, what is confusion? What is diffusion? Anybody remember? Confusion is about how does changing one bit in the key affect the ciphertext? Like how many bits change in the ciphertext? And diffusion is about how does one bit of change in the plain text affect the ciphertext? All right? And as you can see here, this registry thing going on is an attempt to maximize the confusion. All right? We're continuously changing the key all the time so that there is no, so you cannot reuse information about the key. All right? All right. Okay, I don't want to get more into confusion and diffusion about these ciphers, but these are stream ciphers. Any questions about them? All right. So they're done bit by bit or byte by byte, but the point is you're doing them in real time. All right? And each bit or byte gets encrypted in one shot using effectively what is a one-time pad, just an exclusive OR. All right? Any questions? Yes? I will say the most, I don't know about the most famous, but I will say the most popular stream cipher nowadays is probably, I'm going to guess, Snow 3G. It's actually the one that is used, that is recommended now, lately, very recently, for 3G and 4G communications. All right. All the many of the previous ones have kind of are under suspicion that either they are known to be hacked or we believe there are government agencies out there which have hacked them. All right. So that's my understanding as far as I know. All right, for stream ciphers. Okay. Let's talk about a different type of cipher now, other than stream cipher. So the stream cipher is continuously generating the key, but you'll notice it's not doing anything with the plain text. It's not doing anything fancy with the plain text other than just exclusive ORing it. Okay. There's another class of ciphers called block ciphers. All right. So your seat has changed, sir. Don't ask me why. It's just, I'm not privy to that information. Okay. So let's talk about block ciphers. This is a different type of cipher altogether. All right. And these are doing something far more complicated. Okay. The way the block cipher works is this. And maybe I need to draw a picture on the board a little bit. The essential idea of the block cipher is that we take the plain text that we have. Okay. Let's say this is our plain text. And we break it into blocks. So like this. Okay? So these are blocks. So block 1, 2, or 0, 1, 2, 3, etc. So we break it into blocks. How big are these blocks? Depends on the cipher, but let's say the blocks they're not going to be tiny. They're not going to be like 1 byte. They're going to be like 256 bits or 512 bits or 1024 bits. They're going to be in the hundreds or thousands of bits in size, okay? And what do? The block cipher essentially does this. With each block, and I need a new color here, with each block, it divides each block into 2 parts, the left and the right. All right? And for each block, it takes the right hand, this is one example of a block cipher. There's other ways of doing it. But in this example, it takes the right-hand side of a block and it applies a function to it. The function is sometimes called a Feistel function or a round function. And it applies a function to it with the key. So it's essentially encrypting one side of the block. All right, so you take the key, you've got your function here, you kind of encrypt one side of the block, the right-hand side of the block, and then you exclusive OR it with the left-hand side of the block. All right? And in a way, this is kind of like encrypting this block. All right? But it's not done. Once it's encrypted the left-hand side with the encrypted right-hand side, once it's exclusive ORed the left-hand side with the encrypted right-hand side, it does it again. But this time, the encrypted output becomes the new right-hand side of the block, and the old right-hand side of the block becomes the new left-hand side of the block. All right? So the result of this encryption, it's used to do one more round of encryption. All right? And now the old right-hand becomes the new left side of the block, and the encrypted form of the previous block becomes the new right-hand side of the block. It performs the same operation again. And then switches, does it again and again and again for as many rounds as this cipher deems is necessary. It could be 5 rounds, 6 rounds, 8 rounds, 10 rounds, something like this. Okay? What is this doing? In a sense, what this is doing is, it's a little bit like if you take a bucket of water, you put some ink into one side of the bucket, and you just swish it around. All right? It's essentially trying to maximally diffuse the information in this block. All right? By swishing the block back and forth, left and right, encrypting one side, exclusively ORing with the other side, switching it up, doing it again. All right? So in this sense, within the block, it's maximizing the diffusion within a block. All right? If there was one bit, let's say in the beginning of the left-hand original plain text, you have no idea where that is in the ciphertext. In fact, it is not necessary, it's not, you don't know exactly necessarily where it's going to end up being. All right? So within the block, the plain text has been smeared around so effectively you don't know where each bit is anymore. All right? And it's been continuously encrypted and switched and encrypted and switched and encrypted and switched. All right? How do you decrypt this? Well, decrypting this is kind of crazy. This function f, this Feistel cipher function, has a very special property, and you're going to see it in a moment. How do you decrypt this? It looks like we've mushed the information up irreversibly. Well, this is a very special function that does the following. To decrypt it, you start with the ciphertext, right? It's the right-hand block, and the numbers are, it's what was previously the right hand is now the left hand. You take the ciphertext, you put it through the same cipher again. You put it through the same cipher. The only thing is, you now use the keys in reverse. All right? So on the left-hand side, you notice the keys change, K0, K1, all the way to Kn. There's some kind of algorithm to change the keys from K0 through Kn. And now we simply reverse it, and we start with Kn all the way back to K0. And just reversing the order of the keys but running the same algorithm completely reverses the encryption process. And it produces your plain text at the very end. Okay? This is an example of how a block cipher would work. It's just one example of how block cipher would work.
Is the function the same in all rounds?
Yeah, the function is the same in all rounds, on the left-hand side and the right-hand side. So the function has been very carefully designed to have this property. As you reverse the keys, it reverses the whole algorithm. All right, so, which is really interesting. We're not actually inverting the function in some interesting way. We're actually just using the keys in the opposite order. All right. Again, the math behind this, we're not going to get into it, but this is the essential idea. All right, so to encrypt one side, exclusive OR, switch it around, do it again and again and again. The decryption is the same process, just the keys in reverse. All right, yeah?
The number of rounds should be like an odd number?
No, the number of rounds is really determined by the cryptographers. So they will decide like how many rounds is necessary to maximize the entropy of the information, all right? To make it maximally confusing. More rounds is usually better. More rounds is usually better, but at the same time, they also have to take into consideration that you might be using this to, let's say, stream a movie, and you can't like wait like forever for each block of the movie to get sent across the network. So they have to kind of find an optimal number of rounds so that you're using the minimum number of rounds that maximizes that really creates enough entropy, and yet it can be undone in a reasonable amount of time.
Because if it's an even number, the left side will stay
It's true, but but because of this exclusive OR operation, there's no real such thing as left side and right side. The original left and right are not quite the same anymore. Because after you've exclusive OR the encrypted right-hand side with the left-hand side, the output of this exclusive OR contains information about the left and the right. Not, it contains information about both. All right? So in each round, we're really like confusing it up so that the original left-hand side and the final left-hand side are not exactly the same thing anymore at all. Okay? So yeah, that is a very important part of this trick, is that we are really blurring the left and right-hand side as much as we can. Right? So they don't remain distinctly left side and right side. This is an example of a block cipher. Question? The key will be changed. I've not gone through the key function, but there is a function to change the key between the rounds from K0, K1 all the way through Kn, and on the other side you have to do the keys in reverse order. Okay, but yes, there must be a key function that rotates these keys within this operation. Okay, this is an example of a block cipher. And by and large, as far as I know, when you're using the internet, at least, in almost all the encryption you're doing, you're using a block cipher, okay, nowadays. Like I said, stream ciphers, the only place I know them used is for things like real-time, like phone communications and things like that. For the most part, over the internet, we're using block ciphers. Okay. Some popular block ciphers include DES, triple DES, Blowfish, Twofish, Misty, Kasumi, etc. Misty and Kasumi are actually the nicknames of the ciphers used in A53, A52, and I can't remember. I can't remember. Okay, but they were also used in wireless 3G communications for some time. All right. Okay. So this is an example of block ciphers. All right. So do you get the gist of it? Even though if you don't understand exactly the inner workings of it, the idea is we take it block by block, and we're encrypting one side of the block, exclusively ORing with the other side, rotating things around and doing it, and there's a way to undo the whole process as well. Okay, block ciphers. When we use block ciphers, so the result looks something like this, right? So if our plain text was made of 3 blocks to begin with, okay, imagine our plain text had 1, 2, 3 blocks to begin with. These block ciphers are essentially adding confusion and diffusion block by block. So your cipher text, your cipher bits, if you will be of the same size as your as your plain blocks. It'll be the same size, is that each block has maximally tried to add confusion and diffusion to each block by block. All right. So plain block 1 will correspond to I'm calling this ECB block 1. This way of using a block cipher is sometimes called electronic codebook mode. Why is that? You'll notice that this plain block 1, it corresponds to ECB block 1. That's the encrypted version of it. Okay. Imagine for a moment that plain block 1 was exactly the same information as plain block 3. Just imagine that for a moment, okay? Plain block, the block number 1 of your plain text and block number 3 were exactly the same bits and bytes, okay? What would happen? ECB block 1 would be the same as ECB block 3, okay? So that's a downside of this kind of block ciphering technique. All right, and we call this ECB, electronic codebook mode, because it kind of works like a codebook, right? Remember what codebooks are? Codebooks are where you have every word you want to encrypt. You have a book that tells you this word corresponds to this code. This word corresponds to this code, right? That's how a code book works. We saw that last week. This is like a code book because this plain block 1 corresponds to this ECB block 1. And if you have that same block again, it'll have the exact same output. All right, so it's kind of like a code book in a sense, where you can think of it as a book where every block has a code, but we have a function that kind of finds out the encrypted version of it. Okay. This is a problem, and to resolve this problem, well, the problem is that the blocks are now distinct. So if 2 blocks repeat, the encrypted 2 blocks will also repeat. Okay. How can we solve this problem? So the problem here is we have not maximized diffusion between the encrypted blocks, just within the encrypted blocks. All right. And I'll show you an image really quickly of why this is a problem. If you do this on, I don't know, text information or some other kind of data, maybe it's not a big deal. But in some types of data, this is a big deal, and I'll show you an example of this. Imagine we take this picture. This is Alice in Wonderland, I suppose. This is Alice, okay? And we encrypt this block by block. Every block, like this block right here, will get transformed into this crazy looking block right here, okay? Which is great. However, if we do it block by block and the blocks are small enough, this is what the encrypted version looks like. You can still see Alice. You know, you've encrypted the whole thing, but you can still see Alice because the blocks are small enough relative to the overall data that is still meaningful at this resolution. Now, this might only be true of some types of data, like video, music, you know, like video, audio, something like that. Maybe it's not that useful for other types of data, but you can see the risk, right? If you have a lot of repeating plain blocks, you're going to get a lot of repeating code blocks. And that's a problem. We cannot we can say, yeah, we've you use state-of-the-art encryption. Oh crap, even a child can see what it is though. All right. To resolve this, there is other types of ways, other modes in which we can use block ciphers. The same cipher, we just combine it in different ways. So this is called, I'll show you an example called CBC, or cipher block chaining. The word blockchain kind of comes from this mode, all right, in a sense. So cipher block chaining, this is long before we had cryptocurrencies and blockchain, but this is where blockchain begins from, all right? So cipher block chaining looks like this. Same idea as before. We take block 1, block 2, block 3. We perform the encryption on block 1, block 2, block 3. All right? Now here's the trick. Rather than simply taking the encrypted blocks as if they are the final blocks, we perform one more action on them. When we have encrypted and produced cipher block 1, what we do is we exclusive OR it with what we call an initialization vector. This is just a vector of random bits that the cryptographer has chosen, or the person encrypting this has chosen, just a set of random bits, okay? So we exclusive OR the first cipher block with the initialization vector, and we get what is called CBC block 1, okay? Now, what do we do for plain block 2? We encrypt it all the way down to cipher block 2, but now take a look at what we're doing. We're now exclusive ORing this with CBC block 1, with this block that we created before. All right? The result is what we call CBC block 2. So what does CBC block 2 have? It's got very high entropy version of plain block 2, right? Maximum confusion and diffusion. But it also, because we exclusive ordered it with CBC block 1, it also contains information about CBC block 1 in it. All right? So the information of CBC block 1 has been smeared, it's been spread into CBC block 2. And we do the same thing down the line. Cipher block 3 gets exclusive ORed with CBC block 2. So CBC block 3 has information about CBC block 2 in it as well. But CBC block 2 had information about CBC block 1. So that means CBC block 3 has information about both these blocks in the final block. All right? We're spreading this information all the way down the line. And this way, no two blocks will be exactly the same. If we go back to that image of Alice with ECB block with electronic code book mode, we had this problem. With CBC, we have no problem. All right? Every block gets information from the previous block within it, in its DNA. All right? And then this gets spread all the way down, so no block looks just exactly like a previous block. It cannot. All right? So this is like two blocks, two modes of using. So these are called modes. These are two modes of how we use blockchain ciphers. All right. So I've shown you ECB mode, and CBC mode. All right. In the beginning, when we created when we first invented block ciphers, people largely maybe used ECB until people found out very quickly this is a problem. All right. So remember, never use ECB mode. You should always use at least cipher blockchaining, CBC mode. There's several other modes. There's like dozens of other modes out there. I'm not going to go into all of them, but they're all essentially trying to do the same thing. They're trying to smear information around between the blocks somehow. Okay. In this case, in cipher blockchaining mode, we're smearing it from left to right. There'll be other modes where we smear it between, like, more randomly between the blocks, not necessarily just left to right. Okay. Maybe a block from the right can be suddenly brought in and to modify a block on the left even is possible. Okay. So this gives you a quick rundown of how modern block ciphers work. All right. So we have this kind of rotating system to encrypt block by block, and then we have to figure out a mode to potentially chain blocks together to maximize the diffusion across all the blocks. All right. Quick rundown of how blockchain ciphers work. Not blockchains, of how block ciphers work. Yes, Ed, did you have a question? I noticed a restless hand. No? Just restless hand syndrome? Okay. Okay, anybody else have any questions? Cool. The cipher you saw for your homework, I believe, is an example of a block cipher. All right, it's the AES cipher. It's sometimes called the Rindell cipher, just because it was this was the original name of it before it was part of a competition. There was a competition by the United States National Security Agency, their top intelligence agency, to create a public, modern block cipher competition. And this Rindell implementation, the one that you saw for your homework, is the one that won the competition. Okay. Interestingly, the NSA did not use the exact Rindell cipher. After the competition was over, the NSA told the world that, guess what? We found a slight weakness in the Rindell cipher, and we're going to fix it. And so they publicly gave their cipher. They gave a slight change to the Rindell cipher, and they said, this is our fix to the cipher. It makes it more secure. And a lot of people are scratching their heads going, really? Are you sure you didn't make it less secure? Like, we don't know what exactly they did. They did give us a final implementation, but we don't know why the NSA actually introduced that little bit of change at the very end to make it the modern AES cipher. So there's some suspicion over the AES cipher just because the NSA has its fingers in it somehow. All right. That's it. We'll change it a little bit for you. We're helping you. We know how helpful they are, right? Okay. All right. But you saw something like this. You saw a kind of block cipher as well, where information, so you saw an encryption process and a key schedule process in your animation for the AES cipher, right? So the encryption process is encrypting the information. The key schedule process is generating block by block new key blocks. All right, so that's what you saw as your homework. All right. And you saw all these interesting steps here: sub bytes, shift rows, mixed columns, add round key. And for the most part, I looked at the homework, I looked at the quiz. For the most part, you guys and you saw, by the way, this takes about 9 rounds, right? That's the minimum amount that they say you should do to make this really secure. All right, it's about 9 rounds of the same 4 steps over and over again. In each step, you get a different key from a key schedule algorithm, which looks something like this. All right. And you see the heavy use of exclusive ORs all over the place, right? Okay. So I hope one thing you were able to appreciate by looking at this is, by and large, even though you may not get the big picture, why are they doing all these things, you do understand what each of these steps are, essentially, right? Essentially, the sub-byte step is kind of like a codebook cipher. We're just looking up a table called the S box, and we're just substituting blocks, bytes of information from a codebook of kinds. It's kind of like a codebook cipher, all right? The shift rows step is kind of like a transposition cipher. It's not a double transposition cipher, but it's transposing row by row or something like this, right? So it's like a transposition cipher. Mixed columns is kind of like what you did on the Lund validator, kind of. It's a modular multiplication. Okay, it's a modular multiplication. And the last step was the add round key. This was an exclusive OR operation. It's kind of like the one-time pad. Except the good thing is that you're assured to get a different key each time because of the key schedule function. All right? So all the stuff that you've learned, substitution, permutation, transposition, modular multiplication, exclusive OR, it all comes together in this very modern cipher. And when we talked about it last week, each of these ciphers had a kind of a problem with it, but it was good and bad about some things. This puts it all together to get the best of all of them. All right? And that produces this block cipher called the AES cipher. And AES is still today pretty much the state of the art. There's some suspicion around it because of the NSA's involvement in not just picking the cipher, but in changing the cipher at the very last moment. But it is still considered like pretty much state-of-the-art cipher for all of us to use. And it is used heavily in any device that you have that offers any kind of encryption. If Dropbox tells you, hey, we are encrypting all your data, they're probably using the AES cipher. If you go down to Nova and you buy an encryptable hard drive where you can set the key and it encrypts it in real time for you, it's using the AES cipher. All right? It's used heavily wherever information needs to be encrypted and particularly stored. Okay? The AES cipher. All right, cool. Any questions? So, and all this stuff that I've showed you, why did we have to go through all these complicated things? Like, why not just settle with a stream cipher? Why make a block cipher? Why make more complicated block ciphers? Why have a competition to find the best block cipher? It's all because of my first slide, which is that we are in an arms race. People are making and breaking ciphers every single day. Well, every single month, maybe. So we are continuously trying to improve the state of the art of ciphers. But now here's the cool thing. All the ciphers we use today, they all appreciate this principle we studied last week called Kirchhoff's principle, which is the cipher should not be secret. If you're depending on security by having a secret cipher, you're probably screwed. The cipher should be designed in such a way that knowing how the cipher works doesn't actually help you. Okay, and so nowadays, the whole art of this art of cryptography is largely open source. Like it's completely open. Cryptographers release ciphers into the public. Other mathematicians try to attack it and see how to take it apart or how to crack it. If they can't, we use it. If they can, we preferably don't use it. All right, so this is a very open game. I don't think there are very many people in the world who can confidently, even government agencies, who can confidently create a cipher by themselves that they think is not going to get cracked. The best way to make sure your cipher doesn't get cracked is release it to the public, let all the advanced mathematicians out there, who you cannot hire all of them, let all of them kind of try to work on this and solve these problems. All right, so this is the kind of the state of the art, developing new ciphers every day. All right, any questions about these ciphers? All right. Yeah, Stephen.
How do they transfer the key?
How do they transfer the key from the, you go meet in a coffee shop and you give each other the key, I guess. Yeah, that's still a problem we have not resolved yet. I mean, until next week. Just wait to see what cryptographers come up with next week. I'll give you something next week, okay? But for this week, we don't have the solution to this problem. Even if you have a key schedule, you'll notice one step of every key schedule, I don't have it in this diagram, but I have it in this diagram, is you still need an initialization vector, right? You need something that's got to be secret in the beginning, right? So we don't have the answer to that yet. So you still need to go to Starbucks and like exchange keys. Unless the NSA is listening to Starbucks, oh God. Then we have to go to Hello Cafe in the front of main gate. Maybe Taiwan intelligence agency is listening to that. So I don't know, man. Just can't go to the cafe downstairs because we don't have a cafe downstairs. Okay, that's something I'm still very sore about. Okay. All right. Now, this is part of the arms race, and this is the cryptographer's side of the arms race. This is the mathematical side of the arms race, developing these new types of ciphers. Okay. Let's look at another side of this whole race, which is on the use of these ciphers. How you use the ciphers can also lead to weaknesses that people are going to try to exploit and crack. So apart from the mathematical side, there's another side of it which is increasingly mathematical, which is the applied side of cryptography. And there's a lot of cracks and hacks on the applied side of cryptography. Let me show you some examples. I'll show you two kinds of attacks that are used. The first attack we saw last week, we sometimes call these depth attacks, where you have more information than the person encrypting wanted you to have. An example of the depth attack is, for example, when you reuse a key for two separate plain texts, then Eve, in the middle of the communication, can use your encrypted information to derive information about the plain texts. Okay? So last week we saw, that if you encrypt a plain text, two plain texts into two ciphertexts, but use the same key twice, like you repeat the key, then there's this depth problem where exclusive ORing two ciphertexts is the same as exclusive ORing the corresponding plain texts. Which means if you can guess one of the plain texts, you can crack all the ciphertexts. Okay, so this is kind of a known problem. We talked about this last week in class, right? This problem is true for all the ciphers we have seen today. This problem still exists. Why? Because at the end of the day, all these ciphers we saw are doing a one-time pad. They're doing an exclusive OR operation. So as a result, all the ciphers we've seen today have this problem. You cannot ever reuse your key across two different messages. All right. So this is called a depth attack. And as Stephen said, well, then what do we do? Do we keep exchanging key? Like if I message you today and I use a key, but then tomorrow I want to message you again, what do I do? Like, do we go and synchronize new keys? What should we do about this, right? There's another type of attack that I also want to mention, which I think Ken or somebody asked me about last week in class. It's called a replay attack. In a replay attack, Eve is extremely lazy and doesn't even bother trying to decrypt anything. Eve simply notices that when Alice sends this ciphertext to Bob, Bob does something. For example, when Alice sends ciphertext C1 to Bob, Bob quickly runs to the bank and gets out 1 million NTD. Well, Eve doesn't need to know what the plain text is. Eve knows how to get Bob to go to the bank and get $1 million now. Eve just replays the information. Eve simply says, hey Bob, C1. And Bob quickly runs to the bank and gets out the money, and Eve's waiting outside with a gun and robs Bob. Okay? Very predictable. Okay? So this is called a replay attack. You see, both of these attacks, I mean, they are kind of mathematical, but both of these are on the applied side of cryptography. All right? This is not a problem with the cipher, it's more a problem with how we use crypto texts. All right? And how we use ciphers. It's the human in the problem. So how do we resolve this? I'll show you one solution to resolving these problems. Introducing the nonce. All right? A nonce is a one-time set of random bytes that you use to add extra entropy to your system. All right? So how do you use a nonce? Let me just show you how you use a nonce, and we'll go back to those two attacks I showed you to see how we resolve those attacks with a nonce. This is how you use a nonce. So you want to send information. You have a symmetric key that the other side also has. You have your plain text. You ask your computer to generate a one-time set of random bits and bytes. Just one time. Say, please generate some random information from me, the best as you can. And your computer gives you this random information. And then what you do is in the encryption process, you add the nonce to the encryption. How? That's any way you want. For example, one simple way could be you exclusive OR the key and the nonce together, and that's your new key, for example. Or you exclusive OR the plain text block by block using the nonce. Any way you want, but you add this nonce into the encryption process. All right? And you get the ciphertext that is now a result of a key, a plain text, and a nonce. Okay? On the other side, to decrypt this information, the person decrypting it now must know the key, the ciphertext, and the nonce. And they can decrypt it and get the plain text back. All right? I know what Steven's going to say. He's going to say, but now you need to transfer a nonce. What the hell? You didn't solve anything. Well, let's see how we use a nonce. Okay, so first of all, before I show you how do you understand how it works? It's just some more random information into the encryption and decryption process. But you need the same nonce on both sides, just like you need the same key on both sides, okay? This is how we use the nonce. Depth attacks. Now, when Alice wants to encrypt information, and I should have drawn this a little bit better. Ed, could you send me a note about this later? When Alice wants to send some information to Bob, Alice uses the key that Bob knows, and she creates a new nonce and uses that in the encryption to create C1. Okay? However, what Alice does then is she not only sends C1 to Bob, she also sends the nonce to Bob. Okay? So what you should draw in this figure, if you have the handout in front of you, is what gets sent to Bob is C1, the encrypted text, the ciphertext, and also the nonce. Bob knows the key already. And now with the key, the ciphertext, and the nonce, Bob can decrypt it. Okay? Now, when Alice wants to send another information to Bob, she can use the same key again. Why? Because she's using a different nonce. She just changes the nonce. The nonce, she can send she doesn't have to encrypt the nonce. She can just send the plain nonce along with the ciphertext to Bob. Okay? Bob gets the new ciphertext with the new nonce. All right? What about Alice? What about Eve? Eve is now in problems because exclusive ORing C1 and C2 no longer gives you P1 and P2, because C1 and C2 isn't just the plain text and the key anymore. It's the plain text, the key, and a random nonce each single time. And knowing the nonce does not help Eve at all. Okay, knowing the nonce does not help Eve because the ciphertext has information of all these three things combined. So as a result, if we change the nonce every time, we don't have to change our key every time. So Stephen is happy now. We just have to go to one Starbucks, exchange keys one time, but then each time I send Stephen a message, I send him the encrypted message and my nonce. And he uses the key that he knows, the nonce that I just gave him, and the ciphertext. I just have to be careful never to repeat the nonce. All right? But this is much easier than transferring a secret key. The only thing I have to transfer every time is a ciphertext, and the nonce is public information. Isn't that crazy? And it completely defeats this depth attack. All right? This is the use of a nonce. What about the other attack I mentioned to you, the replay attack? The nonce, the way we used it with Alice and Bob here, it would not work. Why? Because if I send Bob C1 and nonce 1, Eve will just replay that whole attack. She will send C1 and nonce 1 as well, and it's the same thing, right? So the replay attack doesn't work if I use the nonce this way. I have to do something a little bit different, but I can still use a nonce. To defeat the replay attack, now this is super clever and so simple. Alice does not create nonce 1. Bob creates nonce 1. So when Alice wants to communicate with Bob, Alice says to Bob, hey, I need to talk to you. Can you send me a nonce? And Bob sends over this nonce 1. Bob creates it on his computer. There's random bits and sends it to Alice and says, here's the nonce for you to use. Now Alice uses the nonce and C1 and the key and sends the information to Bob. And Bob says, okay, everything's good. Right? What would Eve do? Eve, if she wanted to like send information to Bob, would have to contact Bob and say, hi, I need a nonce. And Bob would go, no, you're not Alice. I'm not giving you a nonce. Sorry about that. All right. Assuming Bob can authenticate that this is not Alice, which is why we'll talk about authentication later this semester. Okay? So by Bob generating the nonce, it defeats the replay attack because the replayer cannot use a previous nonce. They have to get the nonce from Bob every single time. Otherwise, it won't work. The cryptography will not work. Right? This is a really clever little trick. There's 2 ways of using the nonce. Okay? And again, notice these 2 tricks, I was able to explain it to you without any complicated math. This is the applied side of cryptography, where we are using the highly mathematical ciphers, but we are using them in new and intelligent ways to apply extra layers of security on this thing to prevent kind of human attacks in the cryptographic chain. Okay? Yeah.
Where the nonce will be put?
Fantastic. You can just, the ciphertext, like if you have these bits of ciphertext, you just literally stick it on the end and send it as one big message.
So the one who receives, he knows that.
Yeah, they have to know that this part is the nonce, this part is the ciphertext. Yeah. But you just send it as one big string of bits. Yeah. And we'll be doing that before this class is over. Okay. Awesome. So this is the idea behind using a nonce. So just to kind of quickly review what we've done so far, we talked about the arms race of cryptography. We talked about stream ciphers that are producing bit at a time the key. All right? But the problem with stream ciphers is every bit I encrypt and send, it corresponds to the plain bit in the beginning. So it's in the exact same sequence. My plain bits and my cryptographic bits are in the same sequence. Okay? Block ciphers get around this, at least at the block level, by scrambling the information within the block. So there's no longer a one-to-one correspondence of the bits in the plain block and the cipher block, because I've scrambled the blocks. If I foolishly use the simplest form of block mode called ECB, then I have diffusion within the blocks, but not across my blocks. All right? By the way, notice what I'm saying about diffusion here. If I was to change one bit in this plain block 1, all the bits in ECB block 1 would change. Not just one bit. All of them would change. Why? Because of this trick of exclusiving ORing the right side and the left side, rotating it, doing it again and again and again. One bit of change gets alters all the other bits. All right? So this is very good diffusion within the block. Change one bit of this, 1, 0, or 1, one bit of this plain block 1, and this entire ECB block 1 completely gets rescrambled. It just so happens that if the other block, plain block 3, looks like plain block 1, this is an equally scrambled identical block here. So to solve that, we use a different mode of using block ciphers, where we use cipher block chaining, again, where the notion of blockchain comes from. Where we smear the blocks one to the other. This is the simplest form of smearing across blocks. There's other more complex modes where you can take blocks and use a block from the end to re-scramble a block in the left, and all kinds of things you can do. Okay? But this is the simplest mode that I want to explain to you. And what's really cool about this, and we're gonna see this at the end of the class if we have time, is block 2 has information about block 1, right? Because I've exclusive ordered them together. Block 3 has information about block 2 and block 1. Which means, think about this. If I change one bit in plain block 1, I will re-scramble all of these blocks down to the last block. all these blocks will completely change because I changed one bit in the original plain block. Okay? And what's really cool, and I want you to remember this, is the final block has information about all the previous blocks in its memory, kind of. It cannot recreate them all by itself, but it's got it in there somewhere. That information is in there somewhere. It's just that we cannot extract all those blocks from this one block. But it's being affected by all those blocks. Okay? Just keep that in your mind because we're going to see how we can use this in a very powerful way. All right? Cool. All right, so that's blocks, and we saw AES, and now we saw how certain applied attacks, like depth attacks and replay attacks, can be defeated using an applied trick of using a random nonce and you just create a new nonce every single time. Either the encryptor sends it or the recipient sends it first. So either ways, depending on what your threat is. Okay. All right, cool. I've rushed through all this within 1 hour, and I know it's a lot, and I did it on purpose. I want you to appreciate how freaking complicated this world of cryptography is. All right, it's not easy. It's changing. It's an arms race. The ciphers are complicated. There's all, and I've just showed you 2 types of attacks: depth attacks, replay attacks, all kinds of other attacks. Okay, how can you possibly learn all this stuff and everything else you need to do to develop products out there? Like, you could spend your lifetime learning all about cryptography. It's a little too much for us to all appreciate. All right, and it gets really messy. On page 12, I'm just sharing with you 3 stories from 3 different blogs, okay? To show you how experts get this stuff wrong. Forget ordinary mortals like us. The experts screw this up. Example number 1. The people designing, oh, I hope this link still works. I should have double checked it before I came here today. Maybe this, hold on, let me see. If it doesn't work, the integrity interop. What's wrong with WEP? What's wrong with WEP? I may have to change the link. Here we go. I hope. Ooh, I found a PDF of it. I can't find the original article anymore. Oh, this is. Oh, I found the PDF of it. Okay, I'll share this with you on Canvas later. So there's a whole article about. So WEP was a protocol for the early wireless routers that we have all over the rooms. There's got to be an antenna sticking through this room somewhere as well. I don't know where it is. Where is the router for this room? Oh, it's right below you. Okay. All right. Below you. That's not good. All right. And I won't go into it, but what's the mistake they made in implementing WEP? They were using the RC4 cipher. And you remember I mentioned the initialization vector? Like it's the vector, like in CBC blockchaining, it's the vector that you use to exclusive OR the first block, and then you before you chain them all together. They just chose oops, excuse me. Can't control this. They chose an initialization vector that was a little bit too small. They chose 24 bits for the initialization vector, and apparently, and I won't go through the attacks, there was only 16 million possible initialization vector values, and hackers were able to use this information to break RC4, just because they chose the wrong length of the initialization vector. This whole protocol got screwed up, and everyone all over the world was able to crack it. All right. That's a tiny little mistake to make. And I don't blame the WE people for making that mistake. Maybe they should have consulted a cryptographer before they chose that size arbitrarily. Or maybe they did consult a cryptographer. That person made a mistake. I don't know. But do you see how easy it is to make a mistake? Like one mistake, the whole protocol is gone. All right, so WEP is irreversibly broken because of that single wrong choice. Popular security libraries get it wrong. Please tell me this link still works. Okay, great. This is a link by Alex. Yes, by Alex, my good friend Alex. All right. But it's a really nice blog, and Alex gives a story about how he was using a cryptographic library for Python called Beaker. Okay, and everyone was using it. It was one of the most popular libraries for cryptography in Python. Except they made a little mistake. in the implementation of this library. What's the mistake they made? The people writing this library, they forgot to use a nonce. So they used AES, but every time you encrypted something with a key and sent it out, they didn't have a nonce. So as a result, depth attacks, replay attacks, all of these things worked on this. And developers all around the world were using this library happily without realizing it was hugely flawed. Okay? And so this guy writes, please, folks, generate a nonce and use it. Okay? And at the end, he says something else, and maybe I'll get to this, what his suggestion at the end is later on. Okay? So just because you go out there and find a cryptographic library doesn't mean you should use it. In fact, 99% of the time, I would say don't use it, unless you know a cryptographer wrote it. If it's just some random schmo programmer wrote it, don't use it. Even if they say, hey, yeah, we're using AES, we're using a very advanced cipher, don't use it, because as you can see, it's not just about the cipher. It's about how you apply the cipher and apply ideas like the nonce and etc. Okay? And if you get the applied side of it wrong, you're screwed again. You need a cryptographer. You can't just be a programmer. You know, like just a web developer out there. No, don't trust these libraries that are out there. Okay? And it's not just average programmers getting it wrong. Some of the best programmers get it wrong. All right? This is a blog by, anybody know who this guy is? Coding Horror? We saw this before one time. About Me. Who is this dude? Jeff Atwood, lives in Berkeley. Oh, I was just in Berkeley. Who? Yes, this is the guy who created Stack Overflow. So you would think he knows everything, right? But he was playing around with some cryptographic libraries, and he was like, and he was using a .NET library, you know, and he's like, this is not encrypting it properly. Like, there's something very weird in it. And he goes and he does everything the way he's supposed to do it, and it's not encrypting it. All right? And he goes into what was wrong. What was wrong was this. Look familiar? Cipher mode ECB. The cryptographic library he was using was encrypting everything with a block cipher using electronic codebook mode. That's the mode where you don't smear the information across the blocks. So he was getting repeated blocks of information that looked absolutely identical. All right? And he was like, what's going on? And bang. And so even he had to go and like investigate this. Why is it happening? Go figure it out. And say, oh, this is very complicated. You cannot just go out there and use a cryptographic library and assume they got it right. They usually get it wrong. Because it's not cryptographers writing it. Some other web developer out there writing it, or some other mobile developer out there writing it. Okay? So this stuff is complicated, and you've seen all the ways we can make mistakes. So it's not just you who will make a mistake with cryptography. The experts make mistakes. Popular cryptographic libraries out there are largely wrong about how they use cryptography. The best programmers don't even understand crypto, and they have to go investigate when things don't work out right. Okay? Cryptography is incredibly complex, and unfortunately, just being a programmer and being a little bit good at math is not good enough to safely use this tool. All right? This comes as a shock to many people who have not studied any kind of cryptography. Most people don't realize if you just keep reusing the same key, it's crackable with just one lucky guess. Right? People have this magical conception that when I encrypt something, it's nobody can break it. Or, you know, only in the movies somebody has some weird idea of how to break it. Like, it's all fiction. All right? Cryptographic ciphers, you have to use them correctly for them to actually perform correctly. They're not just black box techniques where you just take a cipher, apply it, and everything works out. You've got to use the right mode. You've got to use the right nonce. You've got to randomize the nonce. You've got to use it in the right order, in the right way. And I've just shown you some of the nuances. There's dozens of more nuances like this. It's too complicated for us to use. So I think we can just stop the class today and just cancel the rest of the semester, okay? I give up, all right? I want you guys to just give up hope. I had a student at this lecture several years ago. He works at Facebook now. And he asked me, like, Professor, what should we do? And I was like, just run for the mountains, okay? Just go find a little hut in the mountains and just live there. Like, just get away from all of this. Isn't craziness. So what should we do? Modern crypto is too complicated. All right, there are too many degrees of freedom, if you will. You have to choose the right algorithm. Experts get that wrong, okay? You have to choose the right block mode. Experts get that wrong. You have to choose the right size of key and the right size of nonce. Experts get this wrong. Can you reuse the key or not? It depends on everything else about the cipher. Are you using a nonce or not? Maybe if you're using a nonce and you're randomizing it, you can use the same key again. I don't know. Should we use a nonce? I hope so. What's the size? I don't know. All of this leads to this very simple maxim: don't roll your own crypto, which means don't write your own cryptographic code. Meaning, I'm going to be very precise about this, don't write code don't write your own ciphers, first of all. B, don't even try to write code that puts together cryptographic elements like nonces and other things by yourself, because you can screw it up, right? Leave this to cryptographers. And definitely don't leave this to another programmer. Don't just go Google and find, oh yeah, in JavaScript there's a popular library, I'm going to use it. You need to make sure that library was made by cryptographers, not by random like 17-year-old kids who just figured some stuff out yesterday, okay? Because then you're in worse shape than you began with. And as you saw, popular libraries are not efficient. In fact, there's a lot of bad popular libraries for cryptography out there. It's just people don't know so little about cryptography, they don't realize what they're doing. They think it's like anything else. If it's popular, it must be good. No, 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 no. All right? So who should pick the algorithms and all these parameters? And what should we do when the world changes, right? What if I'm using a library and everyone says this is good, so I use it, but how do I know tomorrow someone hasn't broken this cipher? How do I know tomorrow they don't realize that, oh, the nonce size should be twice as big, everyone changed? How do I know this? Do I have to keep up with crypto for the rest of my life? Like, I'll get nothing else done if this is all I do. There's too much change in the crypto landscape. Programmers are not fit to pick cryptographic algorithms and parameters. Even security-savvy programmers make mistakes. Okay? So what shall we do? Well, let's take a break. Let's go smoke a cigarette and come back and I'll tell you what we'll do, okay? Okay, let's take a short break. Let's please keep it maximum 10 minutes. 7 minutes, go out there, go use the restroom, go now, not 5 minutes later. Stand up, get out of the room, please. I please ask you, please stand up, get out of the room, leave your desk. You can come back in a few minutes and put your head down again if you want, but just stand up now, okay? Thank you. Yeah.
I have a bit of questions.
Cheating, you're coming to me yet.
I look at the data set, it says there's two kind of entities here called ILEC and CLEC.
Yeah.
So I researched ILEC is like somebody who monopolizes the whole market. So
Okay.
is that referring to Verizon?
I don't want to say who it's referring to. I have this data set through a way, so I don't want to mention who it is and what it is. I should have changed those acronyms.
Okay, so I just kind of weird, like ILEC, CLEC, so I just...
Oh, that was your question?
Yeah.
Okay, I really can't say about it too much. It is a real data set. I didn't make it up. Okay, this is a real data set from somebody who actually conducted these tests himself. And he put it on the internet, so I just took it without asking too many questions. And you understand that as a teacher, I also shouldn't